All right, let's get into it. Today, we're going to shrink ourselves down, way down, and follow the incredible journey of a single water molecule. We'll see how it goes from a solid to a liquid to a gas and all the way back again. It's a wild ride that's happening all around us, all the time, on a level we can't even see. I mean, seriously, think about it. You see the ice cubes getting smaller, you see the water, but what's actually going on in there? It's definitely not as calm and quiet as it looks. And that's the big secret. Everything, including that glass of water, is made of these tiny particles that are always moving. You can think of it like a huge invisible dance floor. And how those particles are dancing? Well, that's what determines if you've got ice, water, or steam. Okay, so let's kick off our journey right here with a solid chunk of ice. We're about to turn up the heat and see how our little water molecule dancers start to react. So when water is solid ice, all its particles are arranged in this really neat, organized crystal pattern. Now, they're not totally still. They're kind of vibrating with energy, but they're locked into their spots. On our dance floor, this is like a perfectly synchronized group dance where everyone hits their mark and stays in formation. And now let's bring in the heat. Heat is really just a form of energy. What we're doing is cranking up the music on our dance floor, giving those particles more energy to really start moving. For water, this right here is the magic number. At normal pressure, 0 degrees Celsius is the melting point. It's the exact temperature where the big transformation kicks off. You know, this is where things get really fascinating. If you actually stick a thermometer in a glass of melting ice, you'll see the temperature stays locked at 0 degrees even while you're adding heat. So if the energy isn't making it hotter, what in the world is it doing? And this is the answer. That energy is being put to work. Every bit of it is being used to break the bonds holding our little particle dancers in that rigid formation. This whole idea of absorbing energy without the temperature changing is kind of like water's superpower. It's actually what keeps huge lakes and oceans from freezing solid in the winter, which protects all the life inside. Okay, let's move on to the next stage of this journey. Our ice has melted, and now we've got liquid water. But, oh, we are not done adding energy just yet. So in the liquid state, the particles have finally broken free from their fixed spots. They're still pretty close to each other, but now they can slide, tumble, and just flow past one another. The super organized group dance? That's over. Now it's a crowded dance floor where everyone's free to move around and mingle. If we just keep adding heat, we eventually hit another one of those magic numbers, 100 degrees Celsius. You probably know this as water's boiling point. And just like what we saw with melting, the temperature gets stuck at 100 degrees while the water is boiling. All that extra energy, and believe me, it's a lot of energy, is being used to give the particles that final kick they need to completely break away and escape as a gas. This amazing ability to soak up and store heat is what makes steam so powerful for industry. And on a huge scale, it's how our oceans help regulate the entire planet's temperature. But here's something really interesting. Boiling isn't the only way liquid water can turn into a gas. I mean, you've seen a puddle dry up on a totally cool day, right? That's not boiling. That's evaporation, and it works a bit differently. So here's the deal. Evaporation can happen at pretty much any temperature. See, not all the particles in the water have the same energy. Some are moving way faster than others, and the fastest ones, the really high-energy particles near the surface, can sometimes get just enough of a boost to escape into the air. Boiling is a fast, chaotic event happening all through the water, while evaporation is more like a slow, steady escape of just the most energetic particles from the top. So far, we've just been adding a ton of energy to go from solid to liquid to gas. So what do you think happens if we reverse the whole process and start taking that energy away? Okay, as we start to cool things down, we're literally removing energy from the system. Our super energetic gas particles, the ones that were zipping all over the place, well, they start to slow down. And as these particles lose energy, they just can't fight off their attraction to each other anymore. They start to clump back together, changing from a gas back into a liquid. You see this happen all the time, like when little water droplets form on the outside of a cold glass. That's condensation in action. And if we keep removing energy, the particles in the liquid just get slower and slower until finally they lock back into that neat, organized crystal pattern we started with. They've returned to the solid state. We call this solidification, or, freezing. And just like that, our whole journey comes full circle. The dancers have slowed way down, they've found their spots on the dance floor, and they've snapped back into that tight, synchronized formation, just waiting for someone to turn the music back up. So here's the bottom line. This isn't just some abstract cycle in a textbook. The special way water absorbs and releases energy is happening constantly on a massive scale. It's what powers our entire world's weather systems. So it really makes you think, doesn't it? The water molecule in your glass today might have been in a cloud over the ocean last month, or maybe locked in a glacier for thousands of years. Where do you think its journey is going to take it next?